Hey, good afternoon, everyone. Welcome to today's Symposium, International Collaboration in Innovation of Water Affairs. It's sunny day here at National Tsing Hua University today, and I believe that your mood is as good as the weather, right? So first of all, we are very honored to invite Senior Vice President of National Tsing Hua University, Professor Chang, to give us an opening speech. Welcome.
Okay, thank you very much. Actually, this is not the opening speech, but it's just a short remark. Okay, the Director of International Affairs Office of our national laboratories, and also Dr. Dong, Dr. Dong Ruian is the experts in the field of the water affairs. And as you know, this conference is kind of international collaboration on water affairs. So not only the attendance in this room, but also there are like 40 experts international join us online. Actually, when we talk about water affairs, now in Taiwan, we really face a big problem because we encounter the big drought in Taiwan just right now. There have been over 4 months or 6 months, there's no typhoon, no raining coming. And most of the reservoirs in Taiwan just left like 20% of the water. Okay, we're just really serious lack of water right now. It will really influence our country, not only the people, but the big industries, and also our national Tsing science parks. So we know how important the water affairs, water resource is really influence us. This time, I think this is the first time we really really hope a big typhoon can come in. Okay, actually in general, we try to avoid any typhoon coming to Taiwan. We'll feel very happy if no typhoon will come to Taiwan during the summer. But now we really hope any typhoon can come in and bring a lot of water to us. So I think the water affairs is really a important issue in not only in Taiwan, not only in Southeast Asian countries, but also for all human beings. A lot of people in the world really cannot enjoy the clean water, or just lack of water resource, or even they have water but no clean water. So I think it is a really meaningful collaboration. So I will never see this kind of project or this conference just like a general research conference or just a common research project. I think this is quite meaningful to all of us. So really thank Professor Dong hosted this conference, and really think the support from our National Science Laboratory and our the Ministry of Science and Technology. Okay, thank you very much.
Thanks for Vice President Xing for giving us the welcoming remarks. So next, before we invite the chair, no? Okay. So next, before we invite the chair, I would like to let you know that since the Ministry of Science and Technology official have urgent schedules today, so the original chair of today's symposium, General Director Chu, is unable to attend to give the opening speech. So we would like to apologize on behalf of General Director Chu. So hence, we are very delighted to invite the new chair of today's symposium. Please welcome Director of International Affairs Office at National Applied Research Laboratories under the MOST, Dr. Franz Ming Cheng. Welcome.
Okay, maybe I can take the mask off. We're keeping social distancing. Okay. Yeah, Vice President Xin, Professor Dong. Good afternoon, everybody. My name is Ming Chang, and I'm currently the Director of International Affairs Office of the National Applied Research Laboratories, the NALABs, which is the national lab in Taiwan. And I'm also the PI for the new southbound Science and Technology Program Office for the Ministry of Science and Technology, the most in Taiwan. And it is my great honor to act on Director General Chiu's behalf to welcome you all here. During this COVID-19 pandemic, I'm also very pleased to meet you here online in maintaining the network and participating in this international symposium in water affairs. For this, I would like to express my sincere gratitude to many people, especially Director Pong. He is in Australia right now. Later on, you will see he will be the host today, and Ms. Tao from the MOST for their support. And Professor Dong and Professor Lin. Professor Lin now is in Tainan. He will join us online later on for their dedication in organizing this symposium. And the distinguished speakers from Singapore, Malaysia, and Australia for their generous sharing in a minute. And today's topic is international collaboration in water affairs innovation. And there is no doubt why we need to pursue this sustainability of water resources, which contributes to UN SDG number 6, which is the clean water and sanitation. And also the SDG number 12, which is the responsible consumption and production. And these goals hit the needs of many of us, especially in Taiwan, just like Vice President Xin just mentioned. In Taiwan now, we are facing the shortage of water, which is very, very serious in the late 56 years. So how to effectively preserve clean water resources and reuse the valuable water is a crucial issue that our generation has to face. And later on, we would like to learn more from our speakers and also the audience here. As you see that the Science and Technology Innovation Centers, the so-called STICs, is an initiative of our ministry, the MOST. By setting up these STICs, totally now there are 12 STICs centers in these Southeastern Asian countries. And we can understand better the needs of their countries, of our friends in Asia-Pacific region, including South Asian countries, India, Australia, and New Zealand. And today, the symposium is one of the efforts that we take a step further by reaching out from STIC-based country to the neighboring countries. That's why we have a collaboration symposium today from 4 of the countries. And I wish it is a feast of knowledge for everyone here, and enjoy the sharing and discussions. Thank you.
Okay. Thanks, Director Cheng, for giving us the introduction and opening speech. So next, please welcome the moderator of today's symposium, Director of Science and Technology Division at Taipei Economic and Cultural Office in Australia, Dr. Peng Shuangjun.
Thank you for your nice introduction. Ladies and gentlemen, good afternoon. It has been a great pleasure and privilege for me to act as a moderator for this symposium today. And I would like to take this opportunity to thank Tsing Hua University and the NALabs for organizing this international symposium. Yes, due to climate change and the industry pollution, water is now indeed a serious national security issue for almost every country in the world. Today, we have the honor to have 6 water experts from Asia Pacific to share their research, concern, and opinion upon this challenge. Before we start the presentation, please allow me introduce briefly our schedule and the rules of procedure. This meeting is scheduled to last 2 hours. And we have 6 speeches to be presented today. And we have a short 15 minutes break in between and 30 minutes for Q&A after 6 presentations are finished. I might mention to the speakers with one ring, if you have 2 minutes, sorry, each presentation will have 15 minutes, and I might mention to speakers with one bell rings where you have 2 minutes left, like this. And with 2 rings bell when 15 minutes are up, like this. Please try to keep your time limit. And to better control the time, there's no Q&A after each presentation. But please write any questions you have to the presentation in the chat box. We will put them in the read up discussion after all 6 presentations are finished. Now, I'm pleased to welcome our first speaker in this symposium, Professor Zulkifli Yusuf from Technological University of Malaysia. He's a key member of Center of Environmental Sustainability and Water Security at this university. Professor Yusuf will speak to us on challenges and opportunities in making water as a sustainable and a competitive economic sector. Professor Yusuf, please take the floor.
Thank you very much for the invitation. I would like to thank Tsing Hua University and most for the opportunity given. Unfortunately, I cannot open my video. Huh? I hope you are bear with me that I can open, suddenly I can open my video, but I hope you can listen my voice. Can you listen me?
Yes, yes, please.
So very sorry for that. Okay. Can you enlarge the screen because I cannot see the screen as well, the slide.
Yes.
Yeah.
Yeah, no problem.
I cannot see my slide. It's very small there. Is it possible to enlarge that one? Otherwise, I can just stop from, okay. First, I would like to, this is basically the content of my presentation, introduction. I would like to discuss on the issues and challenges in water management in Malaysia. My presentation is not so technical, but the purpose is actually to highlight what is actually the main issues in Malaysia and looking at the opportunity for future collaboration and research between especially between Taiwan and Malaysia. And then I would like to discuss on the technology option and the conclusion. Next slide, please. Next slide. Okay. Next. Okay. This is the major trend in water-related issues in Malaysia. Our population will increase from 32.3 billion in now to about 45 billion in 2050. So most of the population will be living in the cities. Maybe by 2040, there will be 70% of the population will be living in the city. And then demand for water is increasing. Now it's about 20 billion meter cube per year. By 2050, it will increase to 55%. Climate change is, of course, one of the very major issues. It is predicted that climate change will increase by 1.5 degrees Celsius by 2070. And because of this, we can expect more frequent flood as well as more frequent drought. Also rise. Also, we can expect increase in food demand by 6% in 2050. And we will continue to expand industrialization and economic development. The trend will continue until 2050. Next, please. This is the major, if you compare the water sector compared to other utilities, basically the water sector's value is very low. For example, in 2015, the values of water sector, water industry is only 11.6 billion. That includes the water supply plus sewerage services. Compared to, for example, energy, electricity, that is 54.4 billion in 2015, and communication, 145 billion in 2017. But the potential revenue in 2040 is expected to be good if everything according to plan, that will be estimated to be 80 billion ringgit in 2040. Next. I just would like to compare the performance of water service industry in Malaysia compared to other countries in the ASEAN, as well as Australia and New Zealand, as published by the ASEAN Development Bank. Basically, if we look at the ranking, we are ranked third, it's under category 3, compared to Japan, Singapore, Taiwan. Actually, it's under 4. 4 is basically effective, 3 is capable. So basically, if you look at that, the range is from 1 nascent to 5. 5 is basically the model. So basically, this was developed based on the water security issues, particularly on rural household, economic, urban, environmental, and water-related disaster. So very good for Taiwan because it improved so much from 2013, which was placed similar to Malaysia, ranked number 3, but ranked under class 3, but now improved to 4 together with Japan and other developed country in this region. Next, please. Next. I would like to highlight some of the important issues in Malaysia. Of course, the first one is demand for water is increasing from time to time. It is expected that by 2050, the increase is about 55%. More importantly is that we depend so much on surface water. About 98% or maybe 99% in some states depend on surface water, and groundwater and other resources are not fully used. Basically, it's really underused. Next. Pollution is one of the issues. Please click a few times because we need few. Next, okay, pollution, especially the point source pollution, and as well as non-point source, and we have also problem silage from restaurant, from domestic waste and all that, from the kitchen and all that. Next. Beside point source, we are also having problem with non-point source pollution side, and that cause pollution, especially in terms of suspended solids, stability, and all that. So all that actually affecting the quality of water. Next. Next, okay. Beside the conventional or the common pollutant, we are also concerned about the new emerging pollution associated with natural organic matter, endocrine disrupting chemicals, antibiotics, pesticide, and biocide. And that has been detected in some places, although the level is very low, but over long term, maybe the impact of the health could be serious. Okay, next. Important issues in Malaysia with regard to supply is the infrastructure is aging, old pipe and all that. Next, which contribute, one of the impact is high non-revenue water. So basically the non-water is still very high, averaging about 35%, but some state, because the water supply is managed by state, there are 30 states in Malaysia, some state record a very high non-revenue water up to 56%. The reason being old piping, asbestos cement pipe, leaking and so on, under meter, as well as some other factors. But the cost to replace the pipe is very high. It was estimated that in order to reduce 1% non-revenue water, it needs about 1 billion ringgit Malaysia. That was about 8 to 10 days ago estimate. Now maybe the cost is much higher. Although look at the small graph there, even though some of the state actually managed to reduce the non-revenue water, but actually the progress is quite slow. In fact, if you compare with some other cities on the left, we are quite high. We are comparable, almost comparable to Singapore, but to Indonesia. When you compare to Singapore is much lower, 5%. Even some cities like Phnom Penh, Vietnam, actually is recording much less non-revenue water. So I think this is a big challenge for us to improve the water use efficiency. Next. Climate change, next. Click please, okay. There are various issues related to climate change. It was predicted that the temperature will increase. Because of this, evapotranspiration is expected to increase as well. We can expect faster water loss from reservoir and water bodies, more frequent storm, and then increased tropical cyclone. But there is no real increase actually in total amount of rainfall. It's only the distribution. The extreme drought, extreme flood will be more severe and more longer. So another thing is that sea level rise is real. Some of the water intake is already affected by salt water. We have both high abstraction in the upstream as well as increased sea level rise combination of these make the solution become increasingly more and more important. Next. Next. Hello.
Yeah.
Next. Slide doesn't move. Next slide. Hello.
No,
Hello. I can see the slide.
you can't.
Hello.
Chúa,
Can you hear me?
Chúa, can you hear me?
Hello.
Chúa?
Now the slide is back. Okay.
So that's
But-
the announce that the slides that should be back, right? Okay, going back.
Yeah, it's back now. Okay.
Okay, I'm back.
Okay. Go up. Before that. Okay. Okay. I would like to highlight some of the potential technology, which is simple, basically. Common technology that is actually proven to be effective, but we are not yet started on that technology. Next, please. One of them is actually the large-scale remote harvesting. We have tried small scale, but apparently small scale is not rewarding for Malaysia because the tariff is very low. But if we can apply large-scale remote harvesting for commercial building, a community, that is possible. In fact, there is some analysis that should actually, if we use that for commercial building, the ROI will be shorter and it seems profitable. Next. We need to explore also groundwater, since we only use about 1 to 2% of the groundwater, still have a lot of potentials. The safe yield is estimated to be 16.4 billion. But what we need now is to have good groundwater mapping. So I think a comprehensive groundwater mapping throughout the country so that we can plan where is the resources and then how to distribute the resources, and as well as to have good management in terms of safe yield as well as avoiding from potential contamination. Next. Another technology that the government would like to explore is the coastal reservoir, which is basically located at the mouth of the rivers. This is quite new, but I think we can learn from Singapore on the Marina Barrage. That is actually being explored now. So I think also an opportunity to look into the best technology for having coastal reservoir in certain river in Malaysia. Next. Reclaim water. Some of the technologies are already very good. So I think we believe that the reclaim water can be used. Next. Next. Okay. This is actually our study recently on the potential of various alternative resources. We look at the potential of rainwater harvesting, lake, and also reclaim water in Kuala Lumpur. So basically look at the bar graph there. We divide it into 6 zones. So if you combine all the resources, apparently the volume is big and actually can be used as alternative resources for future need. In fact, the reclaim water is already almost basically agreement is almost deal with the company as well as the sewage company to explore reclaim water in Kuala Lumpur. Next. Don't be surprised that actually we also consider desalination, especially in the highly demand area, in the industrial area and all that, because we believe that actually in the future, the cost for desalination is going to decrease. And also in addition to that, the cost to treat raw water is increasing because of pollution as well as the more distant source. Now we have to source from far distant, then we need pumping, we need piping, all that infrastructure is very, very costly. And possibly if the desalination is decreasing from the time in the future, desalination can be it can be economically viable. Next. Besides all the technology, it is important also for us to consider demand management, basically changing the behavior of the people. We are still using quite a lot of water, 210 liters per person per day. still higher compared to, let's say, Singapore 150, Hong Kong 130, UK 150. And of course, the target by the WHO is, I think, about 160, something like that. So basically, we have to work that by changing the behavior. Next, or the consumer. Next, one of the problem for us to difficulty to change. Before that, one step behind. Okay, because our water tariff is very low. It's very low. I plotted the water tariff there. I think Malaysia is among the lowest in terms of the tariff, which is about 0.25 cent US dollar per meter cube. I think this is 2 minutes more already over. 2 minutes. Okay.
2 minutes.
Okay. Okay. Basically, we are paying very low, and because of this, it is very difficult for us to use the water efficiently. For example, the industry is not so willing to adopt to water recycling technology because they feel it is cheaper to pay the bill rather than to invest on water recycling, water use at the factory. So similarly, for the sewerage bill is also very low, also 10 US dollar, 0.1, 10 cent US dollar per meter cube. This is much lower compared to other countries. Next. So basically, the challenge is actually to get the full cost recovery. Our industry is still very much subsidized. The tariff is very low. So I think we need to change the mindset that we have to pay more for water. It's very difficult also to increase water tariff because water in Malaysia is managed by state. Water is a state matter. Sometimes the federal government decided to increase the tariff. Always there is cases that states are reluctant to increase because of most likely political reason. They may lose vote if they increase the water tariff. So this is long-standing issue. How can we increase water tariff to make water industry sustainable economically? Next. So basically, the government has been trying very hard to change the business model. Basically, I think the federal government actually managing the water industry. The resources is by the state. The government established Water Service Commission to manage and to transform the water industry, and also form another unit, to call it asset holding company, to take over the state asset in order for the company to be able to be competitive. But they have to pay the loan. Okay, next. Okay. This is basically the strategies we are moving from to stabilize consolidation as well as inequality, making the industry more sustainable in the financial as well as trying to implement the integrated approach in managing the water. Next. So basically, I have said the water industry potential in Malaysia, we need to transform from basically heavily subsidized to more sustainable in terms of cost recovery. We have many challenges, mainly pollution, increasing demand, and climate change. And we need to explore other resources as well, and not to depend so much on surface water as we are doing now, especially the groundwater, reclaimed water, and so on. And the industry need to move from present functional model to more cost recovery, but need a commitment from the government as well as to change the mindset of the people. With that, I think, thank you very much for the opportunity. I'm sorry for not being able to display my face as well as my screen. Thank you very much.
Thank you very much, Professor Yusof, for your interesting presentation on water management and technological options. Thank you. Yes, if anyone has questions to Professor Yusof, please write it on the chat box. We will put them in our Q&A discussion after the presentation. And the next speaker is Professor Dong Ruian from National Tsing Hua University. He is also Dean of International College at this university. His presentation is entitled Recent Advances in Alternative Water Purification and Recovery Strategy for Sustainable Development. Professor Dong, the floor is yours.
Okay, thank you, Director Pang. Also, good afternoon, everyone, especially our distinguished speakers. I'm Randons, and also thanks Professor Zhu. Actually, Zhu is the key person in Malaysia for water resources management, especially to help the Malaysian government to decide the water policy. So that he has a lot of data talk about the water tariff or the water management in Malaysia. Actually, the case in Taiwan also quite similar, especially in Taiwan at this moment, like our senior vice president mentioned, that now Taiwan faced the very, very severe water shortage during last year and this year. So that's today would like us to talk about the one topic. Since a lot of people talk about a lot of policies, so that's I decided to talk about some technique. Here I would like us to mention about the capacity ionization. This is one kind of the desalination technique. Here, I would like us to tell you some contents here, but should be very fast. And here's myself actually is the chair professor at Tsing Hua University, also the deans of the Tsing Hua International College, also the directors of we call it CERN, names, also the conveners, and also the fellow. I think so we can jump it very fast just to see. Water actually is very important, like everybody mentioned, so that's why we are here to talk about the water issue. According to one speech from the Professor Richard Marley. Richard Marley actually, he was the Nobel laureate in 1996. He mentioned that during that talk, he raised the 10 big problems in the next 50 years. So here you always said that's the first one in 2003. He raised up that the first one is energy, second is water, third one is food, and names fourth one is environment. Up to now, almost 20 years, they still find that the energy and the water is one of the most important issue. Even though for UNDP, they raised the 17 SDGs. Energy and water is one of them. One is in for the goal 6, one is goal 7. So that is the case. So when we talk about the water, you will see that the water actually is not all available. Around the 98% is the seawater or the salty water. We cannot use it. And then another, that's 2% actually is the groundwater and some others. So that means that we only can have around the 0.01% of the fresh water we can use. So it seems quite hard to understand. But it's just the thing about if the global water, 1 liter, equivalent to 1 liter, and how about the fresh water? Just 1 drop of them. Means that you have the 1 liter of water, and then only 1 drop of the lost water we can utilize. And lost 1 drop of the water dropped, we need to supply 9 billion people in the world. So water actually is quite important here. So that's the way we would like us to say that's some facts about of the water. Okay, names if you have interest, you can try to find the website. But here we will see that in 2008, around 30% actually they lived without the safe drinking water. Names in 2050, around 25% worldwide will shortage of water. And at this moment, every 2 minutes, 1 child will die because of water. So this value actually is quite terrible for us. So that's why a lot of people try to talk about the water issue here. And in Taiwan, also the same case here. We mentioned it several times here. So that's this one actually is the pictures of the Salmon Lake at this moment. This one is more terrible. This one is the reservoirs. Okay, in Miaoli County. So that's the Ming reservoir. Previous time, all these are full of water, but now we only can see the sludge sediment here. Okay, so that is the case. And like Joe mentioned, in Malaysia, people use the 210 liters per capita per day. And in the US, maybe 380. And even in those European people, they just use around 150 to 200 liters per day. But in Taiwan, we used 284. We are shortage of water, but people still use much higher names the average one, especially much higher than names Asian country and European country. So that's why we need to think about how to increase the lost water quantity as well as water quality for us. Okay, so that is the most important. So one case here, we mentioned that the water issue is here, 6.1. Named energy is the 7. So the world trend here is that tries to use the energy saving technology so that we can try to use the energy saving technology as well as the energy efficiency is high. For example, for water treatment, like the Professor Zhuo mentioned, we will use some anaerobic NMRs so that they can try to decompose the nitrogen as well as the phosphorus and carbon, and also they can tries to save energy. Sometimes they also can recover some energy. And in addition to this one, a lot of people talk about the water energy methods. We call it wind, or food energy and water, we call it fuel. So all this actually talk about the usage of the water and energy to produce foods, agricultural waste, and some others. And a lot of people also tries to talk about the water recovery. Zhuo also mentioned the case. Professor Zhuo, actually the case in Malaysia and in Taiwan is quite similar. Now we are talking about how to use the reused water and the names, so that's the reclaimed water. So that's the water recovery, recycling, and reuse at this moment is very important. Even though for Professor Lin from Singapore, he will also talk about the membrane technology. So that's today I don't talk about the membrane technology. I only talk about the capacitive deionization, and also have the concepts for CDI. That means that we can use the very cost-effective methods to fabricate the lost material, especially it's quite good for us as well as for our Asian people. Here is the smart wastewater treatment platform. Here you can see that we try to monitor the efficiencies of the wastewater treatment system. So that's we try to do that. But now we try to do the multifunctional technology. Names advanced nanotechnology is one of them. So that's we thanks to the technology because we can prepare a lot of the novel and advanced nanotechnology. So we can do. So that's from this nanotechnology we can do the photoelectrochemical reaction. So that's use the solar cell. So that's we can try to decompose chemical and tries to recover water as well. Names we also can do the capacitive deionization. So we can use the very low energy consumption and then tries to recover a lot of the good water we can utilize. And then we also can try to do the circular economy and zero discharge. Zero discharge is the next steps that Taiwan government would like to do. Especially, we would like us to that all the water can be recycled and can be reutilized. It is very important. So here is the case for the ionization technology like we mentioned previously. We have the lot of methods. For example, membrane is one kind of name. So that's at this moment, the 40 to 50% of the technology for desalination is around the membrane. And then so we still have some other use the multi-stage flash and some others. And in addition to here, we always can see that for the other parts is the capacitive deionization. Why we focus on this only 1% because they need very, very low energy. And the water recovery can be up to around 70%. At this moment, 70%. But for the next few years, we hope that they can increase to around 80 to 90%. And the case is that this technology actually is quite good for Taiwan as well as for the Southeast Asian country. Okay, here's the principles of the CDI. I just use is very simply. We have the two electrodes here. One is positive, one is negative. When you have the voltage, and then some salty water get inside, and the names that they will absorbed by the counterpart. And names when you remove the potential, and names all the ions will get out. So that is the case, quite simple for us. We have some salty water, and then they contain some ion, and names get inside, and then we just let the electrodes to be charged, and names that they will absorb. And then when you remove the potential, and names the ion can be can be regenerated. Okay, yeah. So a lot of people try to develop the carbon, but I talk about the CDI. That's because we can use carbon. Carbon we have been used. We have used the carbon-based material for more than 4,000 years. Okay, from the ancient time, we use the charcoal, we use the wood, the stuff for heating, for cooking. All this actually is the carbon. So that has a lot of carbon material. In the US, you even can find the activated carbon for digestion. If you feel not so good in the US, you can go to the pharmacies to buy the activated carbon. Okay, it's quite expensive here there. Okay, yeah. So we have the different kinds of carbon. For example, 0 dimension, 1 dimension, 2 dimension, and 3 dimensional. So that's they have some example here. So that's there shall be something like here. Actually, you can fabricate at home. Okay, from this. So that is the case. So the CDI concept is quite simple. We try to use the different kinds of the carbon and then tries to name together. So that's we have the salty water here, and then we try to use the carbon as the electron, and then the dirty water or salty water pass through. So that you can see that's the for ion, positive ion, negative ion. That means the cation and ions will be absorbed on the surface of electron, and then the clean water molecules will pass away, so that we can get the clean water here. And the carbon here, you can use the different kinds of carbon. For example, like the hollow nanotubes of the graphene quantum, that's one kind of carbon, and some clay mineral. We can use it very naturally. So that's there's efficiency actually it's quite good. So that it means that 1 gram of our carbon we can try to remove the 1 millimolar of the salt. So the efficiency actually can be recycles the lost waters, and then we can use it. And you can use the different kinds of the ion and the carbon here. For example, you can use the most common as the most famous 2-dimensional and the morph and RGO, and then use the different kinds of the carbon in different electrode. So that's they can try to do sodium chloride and names that they could accumulate a lot and names for conceptual model. You can see that we have the lot of ion, and then when you remove the potential names, that they will all get inside, and the names that they can get out. So that is the case we try to see. Okay. And then going back to the case, we would like us to see why we talk about carbon, because we have a lot of the high value added and biomass derived carbon. Okay, in Southeast Asian country, we have a lot of agricultural waste, pineapples, woods, palm trees. We create a lot of agricultural waste. Okay, it's 2 minutes. Okay, we'll try to do fast. Okay, so for lost biomass derived carbon, you can do a lot of things. And for example, energy materials, photoelectrochemical material, and environment, and some others. So try to think about if we would like us to cooperate with some other, and especially for circular economy, names we try to use some other agriculture, for example, like the ground coffee bean, okay, and sugarcane bagasse, or some pakong here, and then we can grind and then try to fabricate into the carbon. Very simply, we can do it in our backyard. And then they can do it in a very good way. For example, we cooperate with some Philippines friends that they use coconut, and then we try to get it in a very good efficiency. Good efficiency. We try to use the waste, the coffee bean ground. We use the pakong, we use the sugarcane bagasse, and then you can see that the surface area will be much higher than the commercial products. Names, that is the case. If you would like to talk about the possible collaboration with our friends, okay, names you can see that in Philippines, you have a lot of pineapple, coconut, rice husk, and Vietnam, you have a lot of rice, and especially quite famous in coffee. In Indonesia, you also a lot of coffee. Names, Malaysia has a lot of palm tree, Thailand has the rice husk, sugar cane, and even in Nepal, you have a lot of wood. all this actually is the agricultural waste that contain carbon. They also can fabricate the different kinds of carbon-based material, and then we can utilize and we can cooperate, and then you can try to cultivate your own material, especially follows the circular economy. So circular economy is the best biochar actually now is very important, not just only for desalination as well as for wastewater system. Okay, yeah. So the possible application for us is that you can try to fabricate and then try to cooperate with some other guys to do, for example, membrane CTI, or you can use it for energy storage, especially for water splitting. So that is the case when we talk about the water earth reuse and the water's utilization. So the opportunity for us to do the cooperation, especially to do the water energy methods. For example, you can try to have your water and wastewater treatment technology, and names you can try to fabricate your own, especially for carbon-based material. And names you can try to do some others with wastewater treatment, as well as to do the energy storage. And names you can reuse, and names that recover, so that they will get some purified. So that is the case I would like us to mention. And then I also hope that that's from today's presentation and discussion, we can try to find some other good topics that we can cooperate. And finally, I would like to thank them the most for their financial support. Also, our friends from Malaysia, Philippines, and Vietnam for their hard work. Okay, thank you. Thank you.
Thank you. Thank you very much, Professor Dong, for your presentation on water purification and the recovery strategy. And again, if you have any question, please write in the chat box. We will discuss them later on. And the next speaker is Professor Tai Tu Lim from Nanyang Technological University, Singapore. He served as an associate dean of College of Engineering at this university. Professor Lim will speak on water technology and management in the context of smart city and a circular economy. Professor Lim, you have the floor. Thank you.
Thank you for your kind introductions. Can I see my slide? Okay, yeah. Next. I can't see part of it. Okay, so I think Chairman have introduced my background. I would like to talk a little bit more about my research. My research have three areas. First is advanced water and wastewater treatments with particular focus on chemical oxidation using heterogeneous catalysis process. And I also work on photochemical degradation of pollutants. And I have some project on membrane separation using ceramic membranes. And my second area is about nanomaterials for environmental remediations that include catalyst development, adsorbents for pollutant absorption, and solvent for oil water separations and nanocomposite materials. And the other areas I also venture in is resource reclamation from waste to energy and waste to material conversion. I like to say that I'm also the founding editors of the Journals of Environmental Chemical Engineering Elsevier, and these journals have extracted a lot of interest worldwide, particularly from China, India, and also Malaysia, Australia, and Taiwan. Next. This is the outlines of my presentations. I will cover three topics. I start with overviews of research activities in water domain at NTU. Next, I will move to Singapore's water demand, supply, reclamations, and reuse. And finally, I will cover just sharings of what has happened and the current development of digitalizations of water management system in Singapore, driven by the government. Next. Okay, NURI is a cross-university research center focused on environment and water. It has about 300 people, mostly the researchers, including the professors and the principal investigators. Its research can be grouped to 4 areas, namely biotechnology and bioprocesses, environmental chemistry and materials, resource recovery, and membrane technologies. And these research are underpinned by two important thrusts. They are modeling and AI, and engineering and analytics. In my subsequent presentations, I will cover the analytics and also the membrane technologies of NURI. Next. Okay, NURI has a range of the analytical instruments to support environmental analysis, including soil analysis, water analysis, pathogens and toxicity testing, and characterizations of materials, including membranes, polymer membranes, and inorganic materials such as catalysts and inorganic solvents, and also waste materials. Next. Okay, for the water analysis, NURI have recently acquired a range of the high resolution mass spec equipment to analyze micropollutants in water. This includes unknown pollutants. And some of the equipment allow us to detect pollutants down to the concentration range of picogram per liter. To name a few of the applications, for example, as shown at the bottom left of this slide, so some examples of applications include analysis of disinfection byproducts, including nitrosamines and DMA, and THM, haloacetic acids, haloacetone nitrile, and haloketone. And go back to the previous slide, please. Okay, it can also use to analyze off-flavor compounds and also PCB, PAH in water using solid phase micro attractions and pesticide residues in water and food samples. In one of the particular configurations, we can actually combine LC and ICP-MS in hyphenated mode in order to analyze arsenics and organometals in the water down to the PPT level. Okay, next. Okay, about the water research at the NTU NURI. So here are some of the areas that we cover. For water production, we study seawater desalination, membrane fabrications, and membrane modules and system designs and sensors development. For wastewater treatments, we cover energy neutral or even energy positive process. And we also attempt to recover resources such as nitrogen, phosphorus, and energy from the wastewater treatment. And we also explore innovative industrial solutions to treat complex industrial wastewater. On contaminant removal, we develop catalytic redox processes, especially advanced oxidation process with ozones, phantom, photocatalysis, photochemical, or UV-based technology to remove pollutants. And we also develop solvents material to remove anions. On the water quality monitoring and modeling, we also study contaminant fit and transport in water, including groundwater. Next. Okay, so membrane technologies in NTU is mainly championed by SMTC. It's a research center under NURI. SMTC stands for Singapore Membrane Technology Centers. Over the years, we have developed 4 main areas. The first one is to develop novel membranes for forward osmosis, pressure retarded osmosis, nanofiltrations, and membrane distillation processes. It also developed biomimetic membranes, and it has licensed it to a Danish company for commercial production of the biomimetic membranes. The second area of SMTC is to develop the module and also module system design. Some of this involve use of 3D printer. And the next one is development of strategies to control membrane fouling. So, and finally, but not the least, it have a group to develop membranes integrity study, including using sensors to detect membrane foulings that include biofilm development and scale development, and also membrane rupture. Okay, and there are two clusters of photo below just show the equipments that we have and we use to analyze membranes developed. And this includes characterization of hydrophilicity and hydrophobic property of the membranes, and the interfaces energy between membranes and water. And also we have Raman spectrometer, TEM, XPX, and atomic force microscopy to analyze membrane surface roughness. And on the water analysis, to support membrane technology, we have LCOCD to analyze carbon, the molecular, carbon characterization in water. And we have a gel permeation chromatograph to analyze molecular weight distribution in the water. And we also have rheometer to analyze viscosity of the water as a function of temperature and salinity. Next. Okay, one particular membrane which have been developed by SMTC I want to share with all is about nanofiltration membranes. The center have developed a novel nanofiltration membranes which have very high permeability, as you can see in this table. And then it also have a very good separations of divalent and monovalent ions, which is very important for nanofiltration membranes because this functionality allows nanofiltration membrane to be used as a membrane in the membrane bioreactor process, and that will reduce the build-up of accumulations of salt in the bioreactors. And this salt separation property is also important for its application as a pretreatment for seawater RO. And it's operate under low pressures of just 2 bar as compared to the current available commercial membrane, which are operated under the pressures of 10 bars. And SMTC is in the process of commercialize these technologies to the market. Next. Oh, this one, I hope that you can see this clearly. Okay, in this slide, I want to mention about, besides ensuring supplies of safe drinking water, we also aspire to extract resources from the water. This slide shows that we can extract the resources from 3 raw water supply, surface waters from the reservoir, seawater, and at the bottom left is the used water or wastewater, most commonly known worldwide. And then on the right-hand side, you see several green boxes. They are the processes that involve membrane technologies. I can illustrate one example here. If you look at the middle of this slide, seawater. In seawater desalination using RO, there is a reject stream which contains high concentration of sodium chloride. We call it RO brine. And sodium chloride can be used as a source or as a feedstock for colloalkali acid-base production using electrochemical membranes. And this process is important because you can convert chloride into chlorine, which will then be used for disinfection. In addition to this, you also produce sodium hydroxide. And sodium hydroxide can be combined with CO2 capture and calcium magnesium salt separated out from seawater to produce construction materials which are metal carbonates. And in addition to this, we can also use the brine to produce algae, as shown on the bottom right of the diagram. And finally, we can extract phosphorus from wastewater, as shown at the bottom of this slide. Next. Okay, as some of us may be aware of the current use of ceramic membranes. Ceramic membrane has been used in the industry for various processes, including food production. And increasingly, we are using ceramic membranes for the municipal water production. For example, in Singapore, we have used a ceramic membrane to treat surface water into drinking water. And the water plant, accordingly, is the largest in the world that use ceramic membrane for this purpose. And we can actually functionalize ceramic membranes such that it can be catalytic. So in this slide, I demonstrate that we introduce catalyst to the ceramic membrane, and we can actually use ceramic membrane as a microreactor to degrade micropollutants into environmentally benign transformation product or even complete mineralization. Next slide. Okay, now I come to the second topics of my presentation is Singapore water demand, supplies, water reclamation and reuse. On the left-hand side, you see that the current water demands in Singapore, 45% of water are used for domestic sector, for drinking, cooking, and so on, and the remaining 55% for industry and commercial purpose. Currently, Singapore relies on 4 water supplies. Okay, you can see the figure on the right. So these 4 water supply, the first one comes from Malaysia. Then the second one is local catchment area on Singapore Island. And the third one is seawater desalination. And at the bottom is new water. I will talk about new water in the next slide. You look at this water, and currently we have 3, as of 2020, we have 3 desalination plants. And we are going to add 2 more desalination plants this year to increase our seawater desalination capacity to meet 20% of water demand in Singapore. Okay, next. Okay, so this slide illustrates the productions of new water. New water is water that comes from reclamations of the wastewater effluent produced by wastewater treatment plant. In this slide, you show the process trains. You start with feed water come from secondary effluent from wastewater treatment plant. You go through a series of separation process, mainly involve membrane technologies. And the final stage is a RO membrane followed by UV, and that produce new water. So we can also add some oxidant to UV in order to turn it into advanced oxidation process. The user of new water in Singapore is for indirect potable reuse and direct non-potable reuse. Next slide. Next slide. Next slide, please. Sorry, turn 1 slide back. Okay, this slide illustrates examples of the use of new water in demo plant for semiconductor factories. Okay, so after use, we try to reclaim the water using this process series, mainly involves separations and also use of RO membranes. And finally, the treated water is very clean and is good for cooling, and of course, it can be recycled back for the wafer fab fabrication. Next slide. Next slide, yeah, thank you. Now I come to the last part of my presentation about digitalization of water management system. In Singapore, we have gone through a drastic development of digital economy over the last several years, particularly during pandemics. And our water utilities, the PUBs, our National Water Agency, have developed intelligent water management system, IMWS, which have 12 components. And our goal is to realize value creations, better water environments, and improve customer service, efficient operations. And that is enabled by our resilient cybersecurity, the skill force, and the reliable process and technology. Next slide. Next slide. This slide shows the roadmap for Singapore to develop a digitalized water management system. So there are 5 smart systems that Singapore is developing, namely smart drainage grid, smart water grid, smart sewage grid, and smart plants. Okay, and there is one enabling technology, it's called digital operation support. Overall, with this integration, we can improve water load management. Next slide. Okay, we aim to use IoT, data analytics, decision support, and machine learning automations of tasks and robotic to realize digitalization of water management system. As you can see in this illustration, the overarching R&D goal is to reduce energy consumption, chemical usage, reliant on manpower and waste generation, and meanwhile increase water resources and improve water quality. Next slide. Next slide. Next slide, please. Okay. Sorry, go back to the previous one. Okay, here are just two examples whereby digitalization of water management system can save water loss and also can save water consumption. So on top, we show that we use this technology, we can reduce the numbers of leakage to 5 per 100 kilometer per year in Singapore water networks, and non-revenue water loss to 5% versus world average of 31%. And we are going to launch the water saving program whereby smart water meters are installed at household, and we can use mobile app to monitor water consumption rate on the move. Okay, next slide. This is my last slide. If you have interest to know about our work, you can visit this website. With this, I thank you for your attention. I'd like to take this opportunity to thank the organizers for your providing this opportunity for me to speak to your important, knowledgeable audience. Thank you.
Thank you. Thank you very much, Professor Lim. Thank you for your presentation on research and digital water management on NURI. NURI means Nanyang Environment and Water Research Institute.
Right. Thank you.
Now we are going to take a 15 minutes break, and now is 2:35. We will start second session at 2:50. 2:50. See you later.
Okay. Thank you, Dr. Pong. Hi. Okay, we are going to continue on the next section. So I will give my microphone back to our moderator, Dr. Pong. Dr. Pong.
Thank you.
Thank you.
Ladies and gentlemen, we are going to continue our symposium. The first speaker of this session is Professor Cheng. He is Director of Water Effective Technology and Tools, Research Center of RMIT University, Royal Melbourne Institute of Technology, Australia. His presentation is on integrated water management and SDG 6. The floor is yours, Professor Cheng.
Thank you, Professor. My presentation is recorded, so you will be able to hear.
Yep.
Good day, everybody. First of all, I thank the Ministry of Science and Technology, Taiwan, and Professor Saiful Lin for inviting me to this valuable international symposium. My name is Veeraya Jagadhisan. I'm a professor of environmental engineering and the director of Water Effective Technologies and Tools, WET Research Center at RMIT University in Melbourne, Australia. I will begin my presentation with acknowledgement of country. RMIT University acknowledges the people of the Woiwurrung and Boonwurrung language groups of the Eastern Kulin Nation on whose unceded lands we conduct the business of the university. RMIT University respectfully acknowledges their ancestors and elders, past and present. RMIT also acknowledges the traditional custodians and their ancestors of the lands and waters across Australia where we conduct our business. By now, we know the key aspects of the symposium. It is designed to promote transnational cooperation among new southbound partner countries, focusing on water affairs to achieve the outcome shown on this slide. It will be fitting to recall the following quote by one of the famous scientists, Paul Dirac. It will be impossible to answer any one question completely without at the same time answering them all. This is quite fitting to water as well. To answer problems related to water, we have to answer questions related to many other factors as well. Pursuit for better standard of living unfortunately could lead to the deterioration of air, water, and soil environments. Implicit relationships among population growth, urbanization, climate change, and better standard of living could expedite the deterioration. If we consider the water environment, integrated water management has become essential for the sustainable use of fresh water. Innovative and appropriate technologies, systems design, monitoring, all have to be utilized more than ever. The SDGs have been devised wisely to address the issues we discussed and to find solutions. The SDGs have targets to contribute to the sustainability of various ecosystems and their biodiversity. And obviously, water plays a significant role in those ecosystems. SDG 6, Clean Water and Sanitation, has 6 action targets on drinking water, sanitation and hygiene, water quality, water use efficiency, integrated water resource management, and water-related ecosystems. And there are 2 implementation targets on international cooperation and participation of local communities. The figure here shows that the target on integrated water management contributes to all other action targets of SDG 6, either directly or indirectly. Integrated water management looks to find alternative water sources to preserve fresh water reserves for many future generations to come. It looks into harvesting rainwater and stormwater, reusing treated wastewater, and desalinating seawater and brackish water. It also tries to recover other resources such as nutrients from wastewater and salts from desalination brines. So, how the technologies can contribute to integrated water management? We can have a quick look at them in the next few slides. In this slide, I just want to emphasize how important it is to keep the freshwater environment clean. Introducing pollutants such as active pharmaceutical ingredients and algal toxins have clear connections to the presence of antibiotic-resistant bacteria and also to the diseases such as Alzheimer and motor neuron. This shows the need of appropriate technologies to remove persistent organic pollutants and nutrients. Many communities are starting to use low-capacity desalination plants and looking for cost-effective options. They also try to utilize renewable energy and find options to manage the concentrates. Large desalination plants can be run with negative operating costs if salt and energy recovery are practiced. This could be an area where our expertise can be utilized. This slide shows the theoretical feasibility of running a large desalination plant with negative operating costs. Details of it can be discussed later if you are interested. There are 5 large desalination plants in Australia. They do not have any salt recovery systems. And our preliminary study shows some of them will benefit from salt recovery and others need further investigation. Again, the details of which can be discussed later if you are interested. When we have salt concentrates, we can either recover salt or generate power using the salinity gradient. Separating the concentrates and dilute feed solution by an appropriate membrane can increase the hydrostatic pressure of the concentrate stream, which can be utilized to run a turbine. This slide shows the value of power generation using concentrates. Drastic depletion of water in the Dead Sea has led to a project where the water will be transported from the Red Sea to the Dead Sea. Along the way, it will produce potable water and utilize the concentrate to produce power. Rainwater harvesting is the first and most efficient element of an integrated water management system. It can help to save significant amount of potable water and therefore detailed studies to utilize rainwater is essential. If we move on to stormwater, it is one of the major polluters of rivers, causing shock loading of pollutants and structural damages to rivers. While various stormwater management practices are implemented, they are localized and require integration with wider geophysical and social characteristics of the broader surrounding region. Harvesting stormwater by simply catching from the roofs to advanced systems such as aquifer storage, transfer and recovery should be considered very seriously. This schematic shows how to get fit-for-purpose water from stormwater. By using a series of treatment units, phosphorus, metals, nitrates, E. coli, and organic matter can be removed from stormwater and can be recharged to aquifers. There are still many improvements required in the area of stormwater management. Some of them are working with natural processes to improve the ecology of water bodies, developing effective treatments to remove emerging pollutants, improving the performance of nature-based systems such as wetlands, developing policies to encourage public engagement, and revising the existing regulations. Next is wastewater. The amount of fresh water withdrawn around the world annually for various purposes can inundate the Australian continent by half a meter, Taiwan by a staggering 110 meters. More than 40% of this fresh water becomes wastewater, and 80% of this wastewater is released to the environment without adequate treatment. We can see that 2 actions are in play here. One is excessive use of fresh water and 2. The generation of wastewater. This is a perfect recipe for health and environmental damages. But we have a great solution. Producing fit-for-purpose water from wastewater and thereby reducing both the consumption of fresh water and the release of untreated wastewater to the environment. This is a breakdown of fresh water used and wastewater generated in agriculture, industries, and municipal needs. The data can help to realize the potentials in using fit-for-purpose water in those sectors. Depending on the level of treatment we apply to wastewater, we will be able to produce different classes of treated wastewater. For example, tertiary treatment and pathogen removal will produce Class A water that can be used for human food crops consumed raw and other non-potable uses. Benefits of fit-for-purpose water are numerous. For example, retaining the nutrients in the treated water will help to reduce farm consumption of fertilizers and lower the operating costs of wastewater treatment plants. Environmental flow required for large river basins will be affected minimally. Also, treated wastewater from large metropolitan wastewater treatment plants can be used to sustain agriculture in peri-urban areas. This is an illustration of using fit-for-purpose water in a large development project in Melbourne. Precinct-scale sewer mining plant, along with smart rainwater tanks, can reduce the potable water consumption by 45% and halve the amount of wastewater discharged to the sewer system. We have developed hybrid treatment systems comprising physico-chemical and biological units to produce recyclable water from car wash wastewater, aquaculture effluents, and effluents from mine tailings. Near zero liquid discharge is achieved in Tirupur, India successfully, where effluent treatment plants treat textile wastewater and return back to the mills along with recovered salts in the form of brine and crystals. Although there are clear guidelines for the use of recycled water, along with the availability of advanced wastewater treatment technologies, lack of awareness of its potential as a cheap alternative and community perception on the quality hinders the uptake of recycled water. WET Center at RMIT conducts research and carry out projects to create impact on integrated water management practices. The center, with 31 members from various disciplines, aims to develop technologies and methodologies for managing quality and quantity of water by actively engaging with the community, government, and industry. It also enhances research training of undergraduates and postgraduates to prepare them work ready. The center's research covers the entire water cycle under the following three major themes: water resources and management, water and wastewater treatment and reclamation, biosolids and bioenergy. The center's activities also contribute to many SDGs. Our interactions with various stakeholders allow us to identify the research needs in Victoria State and nationwide. The following have been identified as important research needs: microplastics in water environment, antibiotic-resistant bacteria and genes in water, various aspects of integrated water management, including catchment-based plans and modeling, aquifer recharge. Some additional topics are low energy, low cost treatment technologies to produce Class A water, sensing and monitoring sewer networks, nature-based treatments, impact of bushfire, resource recovery, and waste to energy. We have many national research partners as shown here. We have developed international consortia on appropriate technologies for water and sanitation, resource recovery and concentrate management, as well as stormwater management. We also have collaborations with South American universities through Victoria Government. We have editorship in a journal with Wiley and a book series with Springer. Currently, I am working with my PhD students on the following. One is catchment modeling, another one is pollutants in stormwater, applications of membrane bioreactors, synthesis of membranes, and resource recovery. In order to contribute to integrated water management, it is essential to understand all the issues, establish their links and effects, document the current status, and develop mitigation strategies. To contribute to sustainable development goals, we need to design our research and development keeping SDGs in mind and follow the protocols. We need to follow the nature, think outside the box, and utilize the power of good habits. Our collaboration should be for shared destiny of mankind. I look forward to working with you all. Thank you.
Thank you. Thank you very much. Thank you, Professor Jacobson, for your presentation on integrated water management and sustainable development goals. The sound quality was, I think, in YouTube in Taipei was good, but in our Google meeting, there was some echoing. So the next speaker is Professor Mike Birch from University of Adelaide, Australia. He is also the director of Australia Water Consulting. He will speak on the challenges to enabling access to clean and safe water globally, how to achieve SDG Goal 6. Professor Birch, please take the floor.
Thank you, Director Dr. Pong. Thank you for the opportunity to contribute to the seminar. So the topic of my presentation, as stated, is the challenge to achieve clean and safe water, SDG 6, and I'll give an example of some research at the University of Adelaide that's relevant to one component of achieving SDG 6. Next, please.
Next.
Thank you. Outline of my presentation. I'll talk about SDG 6 and the role of the water sector, so water utilities, and goals that are needed to work towards to achieve SDG 6 and the challenges of these goals, and then finish with some research that's related to supporting SDGs, particularly in the environmental management space. Next, please. The most relevant goal to SDG 6 in the water sector is, as we've had a lot of coverage earlier in the presentation, I'll go quickly through these, ensuring availability and sustainable management of water and sanitation for all. And this could be regarded as a core business for water utilities on behalf of their customers. Next, please. Some utilities in Australia have strong awareness of SDG 6, and it's very clear, and they have aligned their business with SDGs and communicated it to their customers. Other utilities, however, are more reluctant because they see it as a cost to their business and it's not relevant to their core business. But it could be argued that it is very clear that Sustainable Development Goal 6 is central to the operation of water and wastewater business. Next, please. We proposed, with my colleagues, my co-authors, that the goal can be achieved by applying 4 principles. And these have been discussed by other authors as well. Separating drinking water and wastewater, accessing drinking water treatment to remove contaminants, protecting and restoring freshwater ecosystems. This is very important, and I'll talk about that later, and guaranteeing access to water rights. Next, please. Separating drinking from wastewater is the biggest single factor contributing to the increase in life expectancy in humans and advancing public health. So building water and wastewater treatment facilities and infrastructure has enabled communities to develop and flourish. There's always a huge opportunity, further opportunity for innovative water recycling research, which has been, I suppose, a central part of the discussion of this conference. Next, please. Accessing a second goal to assessing and treating drinking water, greater access to high quality water is essential for a productive economy. Now, this is not really an issue for urban Australia, but it is very important and an impediment to growth in rural and remote communities. Water in remote locations in Australia still requires substantial investment in suitable treatment, and there's opportunities for new technology to meet this challenge. Next, please. Protecting and restoring freshwater ecosystems is critical, as there is a close relationship between ecosystem well-being and human health. And most of the world's freshwaters are degraded due to unsustainable withdrawal, contaminants, and climate change and nutrient pollution. So it's important that we focus on enhancing the ecological integrity of our freshwater lakes, ecosystems, and rivers. And I'll talk about that in terms of research from the University of Adelaide. Next, please. And the last challenge is guaranteeing access and water rights. And economic development inevitably requires water resources, but it's important that governments and planners and water utilities, water companies, consider the need of the diversity of water users. And all development has consequences for sustainable development. And the discussions around access to water resources are difficult, but they're not impossible. And it's an important priority for both water companies, but also for governments. Next, please. And the risks to achieving these goals, there are a range of risks, and the main risks, I suppose, are institutional, political, and commercial risks and funding availability. But the other risk, which is very pressing, a major issue that looms over all of these goals, is the current and future climate change, bringing a challenge to water resources and water management. And we're already seeing rapid changes in regional patterns of water availability driven by climate change. Next, please. I wanted to move on to talk about some research at the University of Adelaide that's relevant to, as an example of the importance of environmental water allocations to preserve and enhance natural aquatic ecosystems. This relates to SDG, the challenge to support environmental management to achieve our sustainable development goals. So the project I'll talk about is allocating environmental water to preserve and enhance natural aquatic ecosystems at the mouth of the Murray River in South Australia, which is Australia's most important river system. Next, please. The project is supported by the Commonwealth Government in Australia, and it's largely the work of Professor Justin Brooks, my co-author, and it relates to allocating flow to deal with contaminant and salt transport in the lower River Murray in southern Australia. Next, please. In relation to the transport of to flow allocation to major river systems, flow is important in terms of both removing contaminants and also providing resources. So in highly regulated rivers, which the Murray River is an example, water needs to be allocated to both provide resources and remove contaminants in the form of salt. Salinity is a major issue for this river system, and it's also controversial to allocate water for flow for the removal of salt in this major river system. But environmental water has been allocated, and this is has the main purpose of transporting and removing salt from the basin, but also preserving and enhancing aquatic ecosystems in the lower stretches of the river. Next, please. The major hypotheses related to the Commonwealth's environmental allocation of water, and the map shows the location of the lower part of the Murray River in South Australia. It flows to the sea at adjacent to two large lakes and a lagoon called the Coorong, an estuary. But the water allocation from the Commonwealth increases the mobilisation of salt from the basin. It also increases the mobilisation of nutrients from the basin to the sea, which leads to increased suspended solid loads and phytoplankton biomass passing through the lower lakes, the estuary, and the Murray mouth. And what this does is decrease the rate of salt and nutrient accumulation in the estuary, which is referred to as the North and South Coorong lagoons. Next, please. In terms of salt in the River Murray, 1.5 million tonnes of new salt is deposited in the basin each year by rainfall. So therefore, it's necessary to remove at least 1.5 million tonnes annually to maintain neutral salinity change. Next, please. The Basin Plan, managed by the Commonwealth Government, sets out that salt export objectives should achieve a flushing of the River Murray into the Southern Ocean. And the objective aims to have a discharge of an average of 2 million tonnes of salt from the system to the Southern Ocean for each accounting period, which is each year. And this is a very nice aerial photograph of the mouth of the River Murray and its connection to the Southern Ocean. Next, please. This figure shows that for each year, each accounting period, the amount of salt that's transported from the river to the sea, and it varies from about nearly 300,000 tonnes per year down to 120,000 tonnes this is for the period 2014 up to 2018 and 19. And the percentages below in this figure show that this is the contribution of environmental water, which has been allocated, how much of the salt, the percentage that is removed by that environmental allocation, and that can vary from 8% up to nearly 90%. So the environmental water allocation is essential for the removal of, in most years, for the removal of large amounts of salt, unless there is a high flow year, which was an example is 2016-17, where only 8% of the environmental water was required to remove 1.5 million tonnes of salt. Next, please. And for the 2019 period, 600,000 tonnes of salt were exported from the basin, which is 100% from environmental water allocation, which is a dramatic and large amount of salt that needs to be removed from this basin to maintain the environmental status. Next, please. I wanted to also talk about the research, which is the environmental research for this estuary at the mouth of the river and the impact of salinity. And the way we're tackling this at the university is to look at the impact of the salinity on the microbial communities. And the hypothesis of the research is that salinity will have an impact on the composition of the microbial communities, and particularly on nitrogen transformation and abundance and functional activity in the estuary. So the way this has been studied is to establish a range of sampling locations along the length of the estuary, the North and South Lagoon, and to characterise the microbial community and also nitrogen transformation by this microbial community. Next, please. And what the researchers set out to do is to look at a particular gene called NIRK, the gene abundance and also the cell activity ratio along a salinity gradient. And if you look at these figures from left to right, the gene abundance of NIRK, an important denitrifying activity gene, at high salinity from the left to the right, the gene abundance is dramatically reduced by salinity in this gradient along the estuarine lagoon. So what we've set out to do is to try and understand the NIRK. Thank you. I'll move on quickly. So next slide, please. So the summary of the microbial, I've lost the slides. the summary of the salinity is the most important factor we found that is driving community composition of the factors that were assessed. And hypersalinity affects the key nitrifying gene abundance, which suggests that nutrient removal are overall impaired by hypersalinity across the gradient in this estuarine lagoon. But halo-tolerant and extremophile communities that dominate hypersaline sediments are showing a strong adaptation to this niche. We'll continue this work to look at activity ratios of NIRK in the South Lagoon, which suggests there's a role for these extremophile taxa in nutrient removal processes in this unique estuarine environment. Next, please. So in conclusion, the environmental water that's allocated is essential to export large amounts of salt from the Murray-Darling Basin, and the river flow reduces seawater increase and, as prevented 2.3 million tonnes of salt from entering the Murray mouth in 2019 and 20. And the environmental water allocation also prevents the accumulation of salt in the South Lagoon. But the environment is threatened, and it's important to understand the importance of salinity, particularly in terms of impact on nitrogen flux in this estuarine lagoon, and also the importance of salinity in the improvement of seagrass habitat. Next, please. So I'll conclude by acknowledging a range of authors that's contributed to this research, and I'd very much like to thank the organisers of this conference for the opportunity to present some of this work, and look forward to the opportunity to discussing and collaborating with my colleagues and other colleagues in relation to some of this potential future opportunity. Thank you.
Thank you very much, Professor Birch, for your presentation on challenges and how to achieve SDG 6. If the audience have any question, please write it in the chat box. We will respond to that later. The next speaker is Professor Cai Fu Lin from National Tsing Hua University, Taiwan. He is Vice President of Office of the Research and Development at Tsing Hua University. And we are pleased to have him to present the last topic, water quality in Southeast Asia, challenges and opportunities. Please, you have the floor.
Thank you, Director Pan. Okay, it's my honor to share some of my research and observation for the people in Southeast Asia with you. And next slide, please. Okay, here, this is my outline. I'm going to start with the publication analysis for the participating countries here today. And then I will also discuss about some important research topic or challenges that people are facing right now in Southeast Asian country. Then I'll raise a few case studies in Indonesia and Philippines. Then I'll come back to the opportunity we have. Next slide, please. Okay, I'm trying to show you what are the major drinking water research topic. I kind of search from the database of Scopus and try to find out what are the keyword that people are publishing. And you can see that about 50% of the paper are relevant to both environmental science, medical science, and biochemistry for both Australia, New Zealand, Indonesia, Singapore, Malaysia, and in Taiwan. And then other research topics are also quite similar. So it means that we actually share a very common research interest. Next slide, please. Okay, and this shows you the publication countries, from a previous figure. We see on the one on the left-hand side that in Australia, of course, published the most, paper, followed by Malaysia, Indonesia, and then other countries. And Taiwan was on the list, showing that we do have some, collaboration with these 5 countries in Australia, New Zealand, and Southeast Asia. And for Taiwan, if you take a look on the right-hand side, that Australia, Singapore, Indonesia, Malaysia, and Vietnam and Philippines also share some common publication with Taiwan. And I also put the publication from Philippines and Taiwanese also have some collaboration with them. Next slide, please. Okay, this one try to show that on the left-hand side, this represented the last 10 years the publications kind of a list on the same between Taiwan and other country. And on the right-hand side, it shows the from all the publications from the history. You can actually see that they are very similar for publication together with other countries. That means what? That means all our collaboration was happened in the last 10 years between Taiwan and all other participating countries. Next slide, please. And this shows the word cloud for those keywords between Australia and Taiwan for the publications, and actually they are very similar. And the next slide, please. And this shows between between Taiwan and New Zealand, Singapore, Malaysia, Indonesia also share a very similar similar word cloud for keywords. Next slide, please. But the thing I would like to share is actually this, based on the publication keyword, the key pollutants and key technology studied are listed here. If you take on the left-hand side for the pollutants, the arsenic is actually among the common interest for all the countries, listed over here, and lead is the common is a common topic between Taiwan and New Zealand, Indonesia, Singapore, and Malaysia. And a few other common interests, including microbiology and cyanobacteria and E. coli. And for technology, disinfection and adsorption are the two technology that people are trying to study the most. Then others, including chlorination and oxidation, are also common interest for between Taiwan and Australia. But if you take a look at New Zealand, Indonesia, Singapore, Malaysia, I think the desalination and membrane are the other two important topic. And actually, I think Singapore is very kind of strong in desalination and membrane. So this is probably one of the reasons that are on the top list. Next slide, please. So that was based on the literature study, and then come back to another data source. In the last 7 years, I have run a training workshop for the scholars and water professionals from Southeastern Asian country. Totally run about 7 training workshop. About 180 people participated in those workshop. That covers the most Southeastern Asian countries, as well as New Zealand, Australia, and also South Korea. Next slide, please. So in each of the workshop, after the 9 days of lecture and field visit, we always run a presentation to share our own observation of the issues. So what are the common challenges that proposed by the people who participate in those workshops? Including laws, regulation, and enforcement are needed. So that means law and regulation are enough, and we also need more enforcement for water quality problem. And then the background monitoring information are not enough. So this people need want to have more kind of resources to do this, and also more research funding and technology are needed. And also the last and the most important one is education and environmental awarenesses are always mentioned by those people who participate in the workshop. Next slide, please. And this shows the common some of the issues mentioned by different participants for drinking water issues, including climate change, source water protection and acidification, and unstable water supply, and no enough coverage for rural area, and also sludge treatment and water losses. Some of them has been mentioned by Professor Lim, from Malaysia, and then also water quality monitoring, seawater intrusion, and the last one is about the common water quality issues such as stability, ammonia, arsenic, algae, and cyanobacteria, harness, fluoride, manganese, and metals. We'll discuss this more. Next slide, please. And also another issue is about groundwater, because groundwater serve as the water resources for many countries. So they also mentioned about groundwater, such as from natural pollution sources that is include arsenic, fluoride, iron, and harness, and some from industrial pollution such as petroleum mining and cadmium, and also from household pollution such as fecal coliform and septic tank, and also agricultural pollution such as nitrate and pesticides. And also another important issue is acid mining drainage, because this happens in many countries. And also seawater intrusion for those groundwater near the seashore or the river near the seashore. And also landfill and leachate. Next slide, please. So now I want to share about 2 case studies in the Philippines and Indonesia. And this is one of the important water resources in Philippines near Manila. It's the second largest lake, freshwater lake in Southeast Asia called Laguna de Bay. And the area is about 900 kilometers square. It serves as important water resources for two water treatment plants near Manila City. And if you take a look on the right-hand side, this shows the sampling result we have, and the concentration of microcystin and MIB, which is the case of nodal compounds, are very high. Next slide, please. So this lake shares as the fisheries, municipal water supply, irrigation, flood reservoir, transport route, power supply, recreation, and industrial cooling. Actually, on the left-hand side, you see that that's the sample. When we visit Philippines, you can see it's very green. It represents cyanobacteria in the water. And also on the right-hand side, you see a small cottage in the photo. Actually, the people who grow the fish are living in the lake. And the photo shows the fish farm. They grow tilapia and milkfish in the lake, so which could produce a lot of nutrient for the lake. Next slide, please. And because of this, multi-purpose problem and catchment control, so the eutrophication problem is getting worse and worse. If you take a look here on the right-hand side, these are the phosphate concentration as well as the nitrate concentration. These are the 2 important nutrients for the reservoir. And you can see that it's getting higher. So represent eutrophication is very important. Next slide. And they also have a change of the land use. So the industrial development has actually increased the area to be unprotected. And on the right-hand side, you can see that the silting is also getting worse and worse. So the available space or capacity to store water is reducing. Next slide, please. And for Indonesia, the improved water resources for the people in Indonesia actually includes both surface water as well as the groundwater. And for example, here shows that for the about 30% of the water are actually coming from the groundwater. And also in the rural area, 80% of the people do not have safe water to use. So both water resources as well as the water capacity are very important for Indonesia. Next slide, please. And not just the groundwater, but also the urban water utility. This shows the Surabaya. Surabaya water utility is the largest water utility in Indonesia, and the city is the second largest city with the 3.3 million population. And then, next slide, please. And you see the raw water quality they have. You can see the turbidity actually increased, regularly, especially during the rainy season. It could be more than 500, for much of the time. And also the COD constraint is also very high, could more than 20 to 30 ppm, and the DO constraint is very low. That means they have some reducing agents in there, including such as ammonia as well as the organic pollutants. Next slide. So we mentioned about a lot of challenge. Now back to the opportunity we have over here. Many of the technology that need to resolve those issues has been applied in Taiwan already, including the high turbidity treatment, cyanobacteria monitoring and treatment, ammonia removal, and water quality monitoring technology. Next slide, please. So for example, this slide shows during the typhoon season, the turbidity is very high in Ximen Reservoir. So we have a lot of experience on facing this kind of high turbidity issues. Many of our water utility are able to treat the turbidity higher than maybe 3,000 to 5,000 NTU. Next slide, please. And also for ammonia treatment, in the last few years, we have studied a system called BioNet. They are able to remove ammonia from raw water. And NCKU have run a pilot study, and this has been enlarged to become a full-scale water treatment plant in the Kaohsiung area. The capacity is about 300,000 cubic meter per day. It was in commission in 2016. Next slide, please. So since the operation, you can see that the ammonia removal was higher than 96%. So which make water become available for raw water sources. And also the COD removal and DOC removal are also relatively okay. Okay, next slide, please. And last part I'd like to talk about is the cyanobacteria toxin and Desalination compound. These are relevant to my research. So we have developed, next slide, please. We have developed the monitoring technology, management technology, and water treatment technology. Next slide, please. Next slide, please. Okay, so typically, if we found the cyanobacteria plume, we have to take the sample and send back to the laboratory for analysis. It will take about 1 to 2 days. Next slide, please. And if you use a microscope, try to observe if this is a toxin or Desalination producing cyanobacteria, it's very difficult. For example, showing these two photos, they are the same species. However, one can produce toxin and one cannot. Okay, next slide, please. So what we try to develop, we try to use the molecular technology to detect the gene that are responsible for producing this toxin and Desalination compound. Next slide, please. And then we integrate into a mobile laboratory, and so that we can drive the vehicle to the field and do the analysis on the field and report the data to the water utility about in 2 to 3 hours. Next slide, please. So this has been tested in more than 35 reservoirs in Taiwan and a few Asian countries, and has been applied for more than 1,000 times. Next slide, please. So, for example, this has been used in Philippines, Laguna de Bay. We have do the sampling for 4 times. Next slide, please. And you can see that this shows the gene concentration as well as the toxin and Desalination concentration. They have very similar patterns, showing that the biomolecular technology can be used to detect those the compounds. Next slide, please. And also we have developed correlation to help us to better estimate the toxin and Desalination compound from the gene detection. Next slide, please. Okay, so with this, I would like to share the opportunity and challenge, for water quality issues in different countries to all of you. Thank you very much. And lastly, I'd like to say thank you to MOST for supporting research, as well as thank you for the organizers, Dr. Cheng and Professor Dong and Dr. Cheng for supporting this workshop. Thank you very much.
Thank you. Thank you very much, Professor Lim, for your presentation, for sharing water quality and a case study of Indonesia and Philippines. Ladies and gentlemen, now we have heard all the speakers on the program. We will proceed to question and comments. And in this part, we hope to respond to the question to the speakers, and then if time allows, we would like to discuss our possible cooperation on topics of common goal and interest in the future. And I think maybe you have already the question raised by audience participants. May I ask our speakers, each of you maybe spend 2 or 3 minutes to answer the question if you have already saw the question. I think the first question raised by the Dr. Dong to Professor you saw.
Should I answer now? Thank you, Dr. Pong. With regard to the non-revenue water, there are a few strategies water companies now doing to reduce the non-revenue water. First is by replacing the old pipe. Most of the pipe used are actually made of cement asbestos pipe, which is after 40 or maybe 30 years, it become rusty and start leaking at all the joining. And so the government and the company is actually replacing that old pipe. That is one. And unfortunately, the cost is also quite high. Not that easy to replace, especially in the urban area when the density is very high with all the road and infrastructure. We have to dig and replace the pipe. So it's very difficult to replace and quite slow the progress. And we also, basically the company is also doing some pressure management. So basically by doing the pressure management, it can reduce the water, non-revenue water. But I would say actually the impact is still slow. So far, the lowest non-revenue water is only recorded in 1 or 2 states, which is about 19% non-revenue water, which is much higher compared to our neighbor Singapore and also other developed countries like Japan. So the work is still going on, and the target actually is to reduce to 20%. Now it's about 35% average for the whole country.
Yeah. Any further question? We have 1 more minute. Any further question to Professor Yusof? If not, we move to the second speaker, Professor Dong.
Sorry,
is there any?
Sorry, Dr. Pong, there's a question from our audience here in the room.
Yes, please.
So I will pass my microphone to him. Yeah.
Okay, thank you.
Thank you for the opportunity. I would like to ask to in the middle. To Professor Saifuddin, I would like to ask, as we know, most of the industrial in Taiwan is focused on semiconductor. I would like to ask, is there any wastewater treatment system that being adopted in the semiconductor industry, and what kind of technology that being used in general now? Can you provide some information for me? Thank you.
So now we move to direct to Professor Saifuddin, please.
Okay. Thank you for the good question. Well, I'm actually I'm not really the expert for the wastewater treatment, but my colleague, here in our university, we do have done a lot of wastewater treatment as well as the wastewater recycling technology. One of the important pollutant or a group of pollutant from the industrial wastewater as the sulfur, containing chemicals such as DMHO, those kind of chemical with odors, and we have tried to use the biological treatment technology to remove or to transfer those sulfur content chemicals, and then make the water to become recyclable. This is the first case study, and this has been applied in a few important semiconducting company here already. And another one is about the nitrogen removal technology, and also we have also developed some biomolecular technology to try to better understand the key gene participates in the removing the nitrogen compounds, and this has also been adopted in several industries, not just the semiconducting industry, but also including such as petroleum chemical industry and also other industry, especially in the southern Taiwan. So basically, we have used a lot of biology, based wastewater treatment technology for the recycling. Yeah.
Thank you, Professor Lim. There is another question for Professor Lim, Nanyang University.
Okay.
Yeah, it's addressed by the Professor Dong. AI and IoT are popular for digital water. What is the progress of AI-based smart water treatment system?
Okay, this part is basically driven by our National Water Agency's PUB, and there was a recent call to develop online monitorings of water qualities and the performance of the water and wastewater treatment plant. I don't know which companies or institutions have successfully obtained the award. What I can share from my perspective and understandings of what is going on in Singapore is increasingly our water utilities, PUB basically, have put in more and more sensors. And then they are for online monitorings. There are a few things it can provide. It provides some data for the data analysis and also for the performance monitorings. In case there is an incident that require rapid response, then this data will be fed to the AI and machine learnings, and they will come up with some AI technology, AI kinds of suggested solution. I think this is an ongoing process, and with the increasing numbers of sensors and digital devices we put in place, then I believe over here we will be able to develop a more intelligent system to manage the water treatments and water supply. Have I answered the question? Basically, in terms of infrastructure, is driven by government, and then individual company can contribute in a small way in the whole ecosystem of water digital economy. Yeah.
Thank you, Professor Lim. And there is a question on Professor Dong, to Professor Dong. Is there any new water technologies applied to Taiwan's industry water? Professor Dong, please.
Thank you for the questions. In Taiwan, actually, now one of the most important technologies that the government would like us to utilize is the technology to remove nitrogen source, because the nitrogen non-metal nitrate of the ammonium actually is very important in industry. So that's now they try to encourage this the companies to develop a lot of good technology. At this moment, we use some biological methods, for example, NMR that I mentioned previously. And second is tries to use the physical methods, for example, use the air stripping. Unfortunately, that they need a lot of energy. So that's now that the EPA would like us to encourage some others, the new methods. For example, they also try to use the capacitive ionization, like I mentioned, CTI. They try to use is to remove the nitrate. Second is that's now, so we try to use the plasma technology. For those the low temperature of for those the non-thermal plasma, they can try this to remove the nitrates and ammonia very, very fast. So that is the new technology now that Taiwan are using, especially for the nitrogen removal. Yeah. Okay.
Okay. Thank you, Professor Dong. And next question to Professor Birch. Has Australian government used policy tools such as tax deduction to change the business culture of state-owned companies that fail to include the SDG 6 in their guiding principles? Please. Microphone, please. Microphone.
Thank you. Sorry. So the government has not used tax deduction or to change the business cultures, but it's the compliance with state-owned companies, including SDG goals in their guiding principles, has been driven by I suppose, the individual culture of the state-owned companies. Like some water utilities are much more strongly environment-minded and have adopted the goals as part of their policies and also communicated it with their customers. I'm most familiar with water utility companies. Other larger, I suppose, companies have also developed environmental policies which don't directly reference sustainable development goals as guiding principles. But I think there's discussion around that, but it's not, I suppose, not enforced or encouraged by the Australian government in terms of policy.
Thank you, Professor Birch. So, is there any question to Professor Jega Tesang?
Any question here?
Yes.
No. Yeah.
Is there a question in audience? Professor Lim, please.
Okay, Professor Jega, I'm very interested in the center you mentioned in RMIT. Could you speak a little bit more about what is your target, for your goal for the center, and how do we collaborate with your center, in the future?
Yeah, thanks for your question. Actually, one of our aims is to develop international collaboration. So that's how these consortia are formed. So obviously, we are having an informal consortia on appropriate technology. And whenever needed, we can communicate with each other. And if possible, we have even done joint proposals and so on. So that is the direction we are going. And also that allows us to see what are the real-time problems there are in various places with respect to water. And we are quite keen to apply integrated water management. So we like to show our colleagues what we are doing and also to learn from them what they are doing so we can implement together. And one of the things with our consortium, you remember, we have appropriate technology. Sometimes in a risky situation, for example, there is a flooding. How you can generate some chlorine on site simply using sodium chloride. Our colleagues from South Korea, they were able to do that one with like a simple kettle, but you put some salt and the electrolysis can produce chlorine. It's a large amount of, say maybe in 1 liter, you can produce 300 milligram per liter. So you can dilute it and you can disinfect and so on. So this is a kind of simple example. So we would like to develop these kind of technologies, not only high tech, but also appropriate. They are cheaper so that that can help in a kind of, situation where things are not going well. So that's our main aim. So that is one thing. And also we are interested in developing some collaborative research activities like a quotatel agreement, having PhD students getting PhDs from both universities. So spend some time in your organization and spend some time in our organization. So that we are doing with South American universities. So those are the activities we are thinking to do through these collaborations.
Okay, well, I'm actually asking this question for the audience.
Thank you.
Thank you.
Thank you, Professor Jega Tesang. Since we have still 2 minutes, maybe you allow one more question to Professor Lim from Nanyang University. Here, Singapore's water policy is coordinated out of the Prime Minister's office, which is presumably why the whole country values water resource even more. And maybe you can see the question. Water is one of the 4 national tabs projected to meet up to 30% of the country's water demand by 2060. So
Yeah, because water is considered strategic asset for Singapore, because a strategic commodity for Singapore. Without a safe water supply, really we not just short of drinking water, we are also short of water to support the industry demand. So this is basically managed top down. Okay, then for UNIST, we are just supporting this national roadmap. And then when we have to increase the water supply to meet the future needs, so we have to conduct R&D in order to increase the water production rates, and meanwhile to reduce the energy consumption and also the waste generations. Okay, yeah.
Okay. Due to the time, I think it's time to close this wrap-up discussion. In closing, I want to thank all of our speakers for interesting and informative presentations and discussions we had this afternoon. And also thank the audience for their attention and their participation. Thank you very much. And I'm going to pass my microphone to Jason to Taipei. Thank you.
Thank you, Director.
Thank you so much. Thanks, Director Wong, so much for hosting today's symposium. And thank everyone for bringing their expertise and experience around the table and engaging in such fruitful discussion. So at the end, please again welcome Director Franz Minji Cheng to give us a conclusion. Welcome.
Thank you all. Actually, this is quite an interesting topic that we have shared during the past 2.5 hours. And this is not my expertise, but I still learned a lot from the speakers, not only the water-related technology and also the management system. So I think there are quite a few opportunities for our future corporations. So before we leave, I'd like to thank you all for staying with us for the entire symposium, especially for the host, the Tsing Hua University, Professor Dong, and our host in Australia, Professor Pong, and all the speakers for their generosity in sharing your valuable knowledge with us. And our program office has a mission to build international cooperation platform for science and technology innovation. With the support of the science and technology divisions of the MOST, there are 3 in Asia Pacific region, 1 in India, 1 in Vietnam, and 1 in Australia. With their support and the sticks, as we mentioned, there are totally 12 of them. And we are proactive in developing collaborations across the borders of the countries and the scientific technology disciplines to build networks and create opportunities. And before we leave, I'd like to do a little bit commercial. As you see, today's organizer, our boss is the Ministry of Science and Technology. Please visit their website. There are quite a few exciting programs for mobility for students and also for collaborative projects funding. And one of the initiative is the NSSTC, which is the New Southbound Science and Technology Collaboration. So this is an interesting website for you to visit, especially our friends, the students from Asia Pacific region. And also the NA Labs. There are 8 national laboratories involved in this umbrella. And we also have the so-called international exchange programs. We invite students to come to our laboratory for their internship. So you are all eligible to apply. So thank you all. Thank you very much. Thank you.
Direction, sorry, would you mind staying here for one more sec? In order to thank Professor Dong Ruian for contributing so much and making this happen so successfully, so we would like to invite Director Cheng to give Professor Dong our thank you gift. Yeah. Okay, please look at the camera. Okay, 3, 2, 1. Okay, one more. 3. Okay, one more. 3, 2, 1. Okay, thank you so much. Thank you. So we have come to the end of today's symposium, and thank you all so much for joining us and your participation today. Have a great evening. Thank you.
Before you leave, we also prepare